We're going to do a related rates problem about a kite being blown by the wind, and we want to know how fast the angle of elevation is changing, where this theta is the angle of elevation. So I have a few preliminary things here. First of all, they tell us that the kite is 300 feet off the ground, and they tell us that the wind is pushing it horizontally. So we need this distance x between vertical and where the kite is now. Because the rate at which x is changing, that's dx dt, and they tell us that is 25 feet per second. So it's a little hard to deal with an angle that's outside of a triangle. But here in green, if I just complete this rectangle by making a vertical here, only it's not green. Here in green, if I just look at this triangle, now my angle of elevation is inside the triangle. It's a right triangle. This is a rectangle, so the height is still 300 feet along the vertical. And this is still x, the horizontal, and we still have that dx dt is 25. Only now this is going to be the picture that we're using, is this green triangle. So we need to come up with an equation that relates x and theta. And the best one is that the tangent of theta is opposite over adjacent is 300 over x. So if we take the derivative of both sides, this is implicit differentiation because we're taking the derivative with respect to t, not theta. Over here, we're taking the derivative with respect to t, not x. So the derivative of tangent is secant squared theta, and then we need to multiply by d theta dt. And on the right side here, this is bottom times derivative of the top, which is 0, minus the top times the derivative of the bottom, which is 1, which doesn't change it, all over the bottom squared. And then we also have to multiply by dx dt. So this is what we're actually looking for, is d theta dt. So I think it would be helpful to rewrite the secant squared as 1 over the cosine squared. And now I could multiply both sides by cosine squared and have d theta dt all by itself. And now I'll multiply both sides by cosine squared theta. And it makes this one go away. And now I have an equation right here for what I want, which is how fast the angle of elevation is changing. That is d theta dt. And now I just need to plug in numbers. So they do tell us, and I'm assuming, because I don't have any other information to go on, that when they say y is 500, they're calling this y. This can't be y because it doesn't change. So let's have this be 500. Using the Pythagorean theorem, we find out that when that's 500, x is 400. And then we can write the cosine of the angle It's adjacent over hypotenuse. So that just equals 4/5, and I need it squared. So the cosine squared of theta is 4 squared over 5 squared. And now I think I have everything I need to plug in. So we have that d theta, the rate of change of the angle of elevation, dt, is negative 300 over x is 400, so 400 squared. Dx dt they gave us is 25. And the cosine squared of theta is 16 over 25. So these are going to cancel right here. And I can plug the rest of it into my calculator. And it turns out that d theta dt is minus 0. Let me double check. Negative 300 divided by 400 squared times 16 is negative 0.03, either degrees or radians per second, depending on what your angle you want to measure it in. So I'm just going to say units per second, where you have to know that these units are either radians or degrees, depending on what units you need to use. And so there's our answer.